Let's talk reaction enthalpies, or heats. So here I'm comparing two hydrogenation reactions that give the same product. So here I'm hydrogenating cyclohexene to give me cyclohexane at a lower potential energy. Here I am hydrogenating 1,4-cyclohexadiene with 2 molecules of hydrogen to give me that same product, cyclohexane. So this distance, this energy distance, delta G, if you will, this delta G is about half of this delta G, which is what you'd expect, right? This is hydrogenating once, this is hydrogenating twice, double the energy. Now, do you think it should make a difference whether the double bonds are conjugated, like over here in 1,3-hexadiene, or not conjugated? If you think about it, we always say that conjugation is stability, right? We would say that this is more stable than that. And the way this would show up is that we would expect this to be a little bit lower in energy than this, because that's what stability means, right? We were saying that it is in a lower potential energy state. And it is. This energy is lower than that energy by about 2 kilocalories per mole. So at equilibrium, if they were at equilibrium, that's about an order of magnitude. So that's not a really small number, but it's not a huge effect either. So again, this is still roughly twice the energy of a single hydrogenation, but yes, conjugation does count for something. This is benzene, 3 conjugated double bonds. So what would we expect of this? I guess one thing I might expect it to be about 3 times as tall as 26, so whatever that is, right, 85-ish or something like that, up here. That's what I might expect. Not only is it not 85 something, it's not even close. It's under 50. This is actually more stable than the conjugated cyclohexadiene, either of these cyclohexadienes. Okay? So whereas we go up in energy here, if we're talking about adding 3 equivalents of hydrogen to benzene, yeah, it's still downhill, but this is shockingly stable compared to the cyclohexadienes. And so there must be some reason why benzene is sort of magically stable. And we have a word to this. We call this aromatic stability, or aromaticity. Right? Aromaticity just means that we've got this conjugated system that's way more stable than we might expect. And to understand why that is, we kind of have to go back to molecular orbital theory. Here's a molecular orbital picture that took me a very long time to draw that I'm not going to spend a very lot of time explaining. So here, let's compare this conjugated triene with benzene. So really, it would seem like the only difference is that in this case, we tied the ends together to get this. If we look at the molecular orbitals, so I'm looking at the highest filled orbitals and the lowest unfilled orbitals, and I've kind of color-coded what the p orbitals phases look like. I get that the color does not show up at all on this video, which really makes me a little sad. But the point here is that if I look at particularly this energy gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, I can compare that energy, which we might call a band gap, to this energy. So here in benzene, these 2 orbitals are the same energy, these 2 orbitals are the same energy. Right? And the gap between them is quite a bit larger than this. So what? That gap has to do with how stable the molecule is, right? Because if all I need to do is promote this electron up in energy just a little bit, it's pretty easy for me to essentially break that pi bond, right? And get to something that almost looks like it has unpaired electrons. So because of the molecular orbitals that we get from benzene, benzene is sort of magically stable, a lot more stable than just a normal conjugated diene. Now you might ask, is this just a property of all cyclic conjugated molecules, right? So what if we looked at a simpler case, cyclobutadiene? Well, it turns out that the orbitals kind of look like this. All of these cyclic systems end up looking like the molecule itself with a point down. So here we have this, and for cyclobutadiene, the orbitals look like that, which is a problem, because how many pi electrons do I have in cyclobutadiene? Well, I've got 2 double bonds, so I have 4 pi electrons. How does that work here? Well, 1, 2, 3. I guess 4 ends up over here. And molecules don't really like to have unpaired electrons just hanging out like that. And so it turns out that as magically stable benzene is, this is actually magically unstable. And you kind of can't make it. This is not a stable molecule. It was made and isolated for the first time at room temperature in like the 1990s. And that's only because we built a molecular cage around it so it had nothing to react with. So this is really stable, but this, also cyclic, also fully conjugated, is really, really unstable, and we can't even make it. So is there a way we can generalize this without drawing molecular orbitals all the time? Yes. Huckel's rule. Huckel's rule. Huckel's rule tells us that, all right, if you've got a system that fulfill these 3 criteria, planar, fully conjugated, and cyclic, right? So a planar system, obvious, fully conjugated. Both those things together mean that, for instance, if I've got some compound like this, this cannot be aromatic because it's not fully conjugated and cyclic, right? I've got an sp3 stopper here and here. So it really needs to be fully conjugated. I need to be able to push the arrows all the way around the ring without stopping, ever. Right? Planar, fully conjugated, and cyclic. Once we fulfill those criteria, we're going to count pi electrons. If we end up with a 4n plus 2 number, so remember, benzene, our classic, is 6, right? So 6 is a 4n plus 2 number. N is some integer, right? So if n is 0, this number is 2. If n is 1, this number is 6, whatever. So 2, 6, 10, 14, 18, etc. Those are good numbers. They give us aromatic compounds. However, if it's a 4n number, the number is cleanly divisible by 4, 0, 4, 8, etc. Those compounds, like cyclobutadiene, are anti-aromatic. Right? So you might be asked to tell whether something is aromatic, anti-aromatic, or this case where we don't even get through, we don't even get there because it's not planar, fully conjugated, or cyclic. We'll call these non-aromatic. Okay, so let's throw out some practice problems and see what we can get. Okay, here are some practice problems. So this one, got 2 fused benzene rings. It is planar, fully conjugated. I can push the electrons all the way around, and it is cyclic. The whole thing is a cycle. And so I can count up my pi electrons, 2, 4, 6, 8, 10. This is 10 electron system. It is aromatic. It's 10 is a 4n plus 2 number. Okay. How about this one? This is an ion, right? It's got a negative charge here, which means that there's a lone pair on that carbon. So it looks different than benzene, but in a lot of ways, it's the same thing as benzene because it has 2, 4, 6 pi electrons in a planar, fully conjugated, and cyclic system. So this cyclopentadienyl anion has 6 electrons. It is aromatic. It's really, really stable and really important in stuff like inorganic chemistry. So when you take 320, you'll hear a lot about that. How about this one? So it looks like it should be planar, fully conjugated, and cyclic, but our count is 2, 4, 6, 8, which is an anti-aromatic number. So what we'll call this one, and we'll be clear with our language, is we'll say it's anti-aromatic if planar. remember, molecules can move. And so if this thing can avoid being anti-aromatic, it will do so. It will avoid being that. And the way that this avoids being anti-aromatic is that it folds up kind of like a burrito, right? Where all of those pi orbitals are perpendicular to each other. All right, so it kind of folds up like this. So we'll say anti-aromatic if planar. But if it can avoid being planar, it will do so. It will avoid being planar. Okay, this one right here. I've got 246 electrons, so it seems like it's aromatic, but I need to slow down and go through here. Is this planar, fully conjugated, and cyclic? No, right? I've got some hydrogens here that are hiding. So this does not get through the first half of this rule, so this is non-aromatic, neither special nor anti-special. How about this one? This one looks really strained and really unhappy, right? It's a carbocation. It seemed pretty reactive. However, planar, cyclic, fully conjugated, right? That's an empty p orbital that's lined up with the pi bond. So it meets all these criteria. How many electrons? Well, it's only got the 2. Hey, 2 is a 4n plus 2 number when n is 0. So this one is aromatic and surprisingly stable. Okay, so again, you want to make sure when we're trying to decide whether something is aromatic or not, A, make sure that it fits these criteria before we go anywhere else, and then we count. Why are we spending time talking about aromaticity? Well, one reason is that it turns out that aromatic compounds react very differently than we expect normal alkenes to react. We saw a little bit of this in our week 1 lab, that nitration experiment, and we'll talk about nitration in next video or the video after. But for now, I want to focus on a few of the differences between these compounds before we sign off here. So, way back to the first lecture, we said that if I have an alkene plus HBr, we grab a hydrogen with the pi bond, we get some cation, which some nucleophile can then come in and grab. So, the analogous case over here, if I do treat this benzene with HBr, I can get this same intermediate, but I won't get this, right? I will not get something with now 2 double bonds and an sp3 and a bromine, right? Because remember, this is way more stable than this, right? Even without the bromine, it's more stable for me to have 3 double bonds in a row here than 2. So even if I do form this intermediate, and I do, I will always, always go backwards, right? This is an equilibrium that lies very, very far to this side and is never going to go backwards. Similarly, if I add dibromine to alkene like this, I end up with 2 atoms of bromine in my product, right? I end up with this trans dibromide. If I treat benzene with bromine, nothing happens, right? This reaction is super fast at room temperature. This reaction doesn't go. However, if I give it bromine and I give it a Lewis acid to make the electrophile more electrophilic, and I heat it up, then I can add bromine to benzene, but not in the way that you think. This reaction gives me 1 bromine on benzene, and notice I still have all my pi electrons here. I did not lose an alkene, right? So it's an entirely different reaction mechanism because aromatics are different than normal alkenes. They're way more stable, and they really want to get back to an aromatic system.